What if I told you that the moment a human sets foot on Mars, their body starts a countdown not to death, not to a new life, but to something far more unsettling, a point of no return, a transformation so complete that Earth itself becomes lethal to them? This isn't a sci-fi plot. This is real science. And by the end of this video, you'll understand why the bravest people in human history won't be the ones who make it to Mars. They'll be the ones who choose to go, knowing they can never come back. Let's talk about what that actually means for the human body. Because the real enemy of a Mars mission isn't a broken engine, a solar flare, or even a meteor. The real enemy is us. The journey getting to Mars is already a feat that redefines extreme. The moon took us 3 days. Mars? Between 6 and 9 months one way. Round trip. Astronauts would be gone for 2 to 3 years minimum. During that entire window, they're cut off in a way no human has ever experienced. Communications with Earth face a signal delay of over 20 minutes each way. There's no real-time guidance, no rescue mission, no emergency evacuation. If something goes wrong medically, the nearest hospital is literally 8 months away. But forget the logistics for a second. Let's zoom in on something far more intimate: what's happening inside the body during every single day of that journey. Because this is where the mission becomes a biological horror story. Radiation, the invisible rewriter. The moment astronauts leave Earth's protective magnetic field, they enter one of the most hostile radiation environments imaginable. On Earth, our atmosphere and magnetosphere block nearly all of the dangerous cosmic radiation flying at us from every direction. In deep space, that shield is completely gone. Mars-bound astronauts would absorb radiation doses estimated between 870 and 1200 millisieverts over the course of the mission. To put that in perspective, that's roughly equivalent to getting over 600 CT scans in the span of 2 to 3 years. Every single day, high-energy particles are passing through their bodies, slicing through DNA strands, damaging cells, and altering biology at the most fundamental level. The consequences are staggering. Cancer risk jumps by 5 to 10%. The cardiovascular system ages by what researchers describe as decades worth of damage in just a few years. The brain, and this one should stop you cold, suffers measurable, lasting cognitive damage. We're talking about memory loss, slower decision-making, and difficulty with complex thinking that can become permanent. The immune system weakens as bone marrow gets damaged. Eyes develop early-stage cataracts. And here's what makes it even more frightening. You can't just add more shielding. Thick metal armor actually generates its own dangerous secondary radiation when hit by cosmic rays. There's currently no practical solution ready for a crewed mission. Radiation doesn't announce itself. It doesn't hurt. But it rewrites the astronaut's body at the molecular level, and that rewriting doesn't stop. Bones and muscles. The collapse from within while radiation does its invisible damage. Something equally devastating unfolds in the skeleton and muscles. And the mechanism is almost poetic in how cruel it is. Our bodies evolved under Earth's gravity. Every step you take, every time you lift your arm, every moment you stand, you're fighting gravity. And that constant battle is what keeps your bones dense and your muscles strong. Remove gravity from the equation, and the body does something logical but catastrophic. It decides those resources are no longer needed. In weightlessness, bone density drops at a rate of roughly 1 to 3% per month. After 6 months, astronauts can lose up to 18% of their bone mass. After a year, up to 36%. A Mars mission runs at least 2 years, meaning potential bone loss exceeding 50%. Let that land for a moment. A healthy astronaut in their 30s could develop the skeletal fragility of someone with severe osteoporosis, a condition typically seen in elderly patients who can barely walk without risk of fracture. The bones most affected are the weight-bearing ones: hips, spine, femurs. Exactly the structures you need to stand on Earth. The calcium released from those dissolving bones doesn't disappear, it floods the kidneys, dramatically raising the risk of painful kidney stones mid-mission. It's a cascade of biological consequences, each one feeding the next. Muscle follows the same downward spiral. Without gravity to resist, leg muscles, back muscles, and core muscles begin wasting away at a similar 1 to 3% monthly rates. Even more troubling, the type of muscle fiber changes. Endurance fibers, the slow burn kind that get you through a full day of activity, convert to fast twitch fibers that exhaust quickly and aren't built for sustained use. Astronauts returning from just 6 months on the International Space Station described climbing a single flight of stairs as an ordeal. After 2 to 3 years, that level of weakness would be many times worse. And here's the critical detail. Even on the ISS, where astronauts exercise 2 hours every single day using specialized resistance equipment, the deterioration is only slowed, not stopped. Some astronauts never fully recover their original bone density after returning. For a Mars astronaut who spends months in zero gravity during transit, then 18 months in Martian gravity, at only 38% of Earth's likely not enough to halt the decline, and then more months in zero gravity on the return, the damage becomes staggering. If this is blowing your mind, hit that like button right now and subscribe, because this next part about what happens to the heart is something most people have never heard before. The heart. A pump built for the wrong planet. Here's something that doesn't get talked about enough. Your heart is a muscle, and like every other muscle in your body, if it stops working hard, it shrinks. On Earth, the heart works constantly against gravity, pumping blood upward to the brain, fighting the pole that wants all your blood pooling in your legs. That fight keeps the heart strong. In space, that resistance vanishes. Studies of long-duration spaceflight show that the heart can lose up to 20% of its mass. It literally becomes smaller and weaker. Simultaneously, fluid dynamics in the body shift dramatically. Without gravity pulling blood downward, fluid migrates to the head and upper body. Astronauts famously develop puffy faces and thin legs. It's not just a look, it's a full system circulatory disruption. The body senses this fluid excess and begins excreting water, reducing total blood volume by as much as 20%. The heart adapts to moving less blood against less resistance, which sounds efficient, until you realize what happens when that heart suddenly has to face Earth's full gravity again. Returning astronauts from the ISS frequently experience orthostatic intolerance, dizziness, blood pressure drops, even fainting when they simply try to stand up. After 6 months, after 2 to 3 years, a deconditioned heart facing full Earth gravity for the first time wouldn't just struggle, it could fail. Layer on top of that the radiation-driven cardiovascular damage, calcified arteries, weakened vessel walls, elevated stroke risk, and you have a heart that has fundamentally been rebuilt for a different planet. The point of no return, so here's where we land. Cosmic radiation that permanently alters DNA and damages the brain. Bones so porous that standing under Earth's gravity risks fracture. Muscles too atrophied to support the body's weight. A heart too weakened to pump blood upward against a full gravitational field. These aren't hypothetical risks, they're the predictable, scientifically documented outcomes of extended spaceflight, magnified to an unprecedented degree by a Mars mission timeline. Scientists are working on solutions, artificial gravity systems, advanced radiation shielding, pharmaceutical interventions to slow bone loss. But none of these technologies are ready. None are proven for a multi-year deep space mission. And the window to solve them before the first crewed Mars missions are attempted is closing. This means that the first humans to reach Mars won't just be pioneers. They'll be permanent residents. Not because Mars is a paradise. Not because they want to stay. But because the journey itself will have transformed their bodies into something that Earth can no longer sustain. The greatest adventure in human history comes with the most profound sacrifice imaginable, the planet you were born on. The gravity that shaped every cell in your body. The home you can see in the night sky. Forever out of reach. That's not science fiction. That's the reality waiting for the first person who looks back at a shrinking blue dot and knows without any doubt that they're never going home. If this hit differently than you expected, share it with someone who thinks Mars is just a cool adventure. And drop in the comments, would you go, knowing you could never return? I'll see you in the next one.